Hey guys, it's Michael with Breaking Concepts, and today we're gonna take a look at this challenge, this differentiation challenge. And I think I really like this question because I feel like this is really testing you the foundation of what you actually know and understand about differentiation. I think this is such an important question to do for you to confidently have a solid foundation in differentiation. And basically, we want to prove that number one, our derivative of an even function is an odd function. Number two, the derivative of an odd function is an even function. So feel free to pause this video and try it out yourself. I'm going to hide myself so you guys can take a screenshot. Before starting, let's recall the two ways that we prove that that's a derivative, right? We know f prime x is a derivative, but what does it stand for? Well, number one, it stands for the limit of h approaching 0, and we have fx plus h minus fx, right? And then which is divided by h. Also, let's say f prime a, right? A, which is a number, we're going to have limit x approaching to a, and then divided by x minus a, fx minus fa. These two formulas are the two way of differentiation works, and actually I'm going to prove it using this A and B equation as well. So stay tuned for the answers. I feel like the idea here, or the main goal, the challenge for you, is to really understand how to do for both A and B, because I found out you actually learn a lot more in terms of the concept, of differentiation and whatnot. So without further ado, let's kind of start and prove A. And I would say for A, proving with method A is actually easier than proving with method B. And you guys are going to see why in the future. Or if you don't agree, feel free to leave a comment, and would be happy to listen. Okay, so first of all, we know that an even function is basically when f minus x. When f minus x, we would have fx, right? The negative sign of the input doesn't really change anything, right? There's an even function. So what happens is if we start, so let's start by differentiating with our limit. So we would have like f prime negative x, and so we would have f negative x plus h, okay, minus our f negative x, okay, and then divided by h. And so we know that this is an even function, okay? This is an even function. So this would just be very simple, f x, because it's an even function. And so I'm going to continue this in blue. So you have f negative x plus h minus, write this one, and over h, and then you have limit h to obviously it's not done, but people might get stuck here. Even for myself, I actually got stuck here. So remember the idea of an even function. The even function is such that when the input of our function times -1, the value is going to remain the same. Okay, remain the same. So what that means is if we have these input and we multiply it by -1, then the output of that value is just going to be the same as this thing. So let's try it out. Let's try it out and see what it means. So we have negative x plus h, and then we multiply by -1, okay? So what we're going to get is x minus h. So x minus h, because by definition of an even function, is going to be equals to negative x plus h in the concept, right, of an even function, or even function. Okay, even function, super important. Okay, so now we can use this limit h to 0, and then we use f x minus h, and then we have minus fx over h. Okay, so this is what the next step is going to be. Remember from the equation of derivative, inside shouldn't be a minus, it actually should be a plus. Right, so how do we do this? Well, actually we can sub a variable. Let's say k is equals to negative h. So now we can do this. So we have f, right, x plus k minus fx. And then we know that k is equals to negative h, so h is equals to negative k. Okay. And so we take the limit this time of k, but not h, but going to be k tends to 0. So here you might be asking, okay, so we know that h is going to 0, approaching 0, so why is k also approaching 0? Well, look at this, k equals negative h. So if h is approaching 0, what do you think k is going to approach? We have negative 0, okay? K is going to approach negative 0, but basically it's just 0. So k is also approaching to 0 when h is approaching to 0, so that's why we can write this. The reason why we want to have k is because we call k a dummy variable, okay? A dummy variable. And that will came in clutch, and you guys can see in a second. So we have this negative sign here. We can just put it here. Negative k 0 fx plus k minus fx, okay? And then we have divided by k. And then because this is a dummy variable, we can actually sub whatever to replace k. So what we can do is we can sub k becomes h. All right, so h to 0, h, and then you have fx plus h minus fx, okay? And that's the idea of dummy variable. So we have a bunch of variable called k here, k, and we're not really changing anything, right? We're just given that, okay, these are k, and maybe today I decided I don't want to call them k, I want to call them h, so we can just change it back to h, simple as that. And so we understand this one is equals to the entire derivative here. If we look at this, what is that going to be equal to? It's just going to be equal to f prime x. So we know that from here, we have the f prime negative x, which is equals to all of these. So we can write our f prime negative x is equals to our negative f prime x. So we proved that the derivative of an even function is equals to an odd function. Okay, so this is the first we use method A. So now let's just try and use method B. Okay, so method B, we're going to use this one. Okay, now we're going to do method B. Method B. Okay, so let me just write the general form here, x to a, and then fx minus fa, and then x minus a. So now we have to find, we have to sub a negative x, right? We have to sub a negative value. Where do you think we should put it? Should we sub it here, or should we sub it here to sub the negative value? I mean, it was super clear in our previous, method A, because you have h, and h is not representing anything. But now we have fx, and now we have fa. Where do you think we should sub our negative value? Well, the answer is actually we should sub it at a. And the reason why is because if you remember from the definition of differentiation, say we have a point A here, and then we have a x is a variable. Make sure we understand which one is variable and which one is not. Variable is actually our x. A is actually our reference point. Reference point is where we take the derivative of, right? So we have an x, which is a moving secant line, right? To this slope form is a moving secant line, and when x is gonna approach. So when x is going to be approaching to a, the secant line becomes a tangent line, okay? So that becomes our slope of tangent. And so making sure that, okay, we are not taking the variable as a reference point, we're taking the actual reference point as a reference point. So we know that our f prime negative x here, right now, is going to be our reference point, okay? It's not going to be a variable. This is a move. Whatever is inside is our reference point, so it just stays the same. So this, right? These two terms, we're not gonna change it, but we're gonna change the reference point, which is where we want to know the slope of tangent is going to be. So this time, instead of saying f prime x, we can just say f prime negative a is equals to negative f prime a. So a is all values, okay? So all values. Okay, so we can actually try this, okay? So I hope that makes sense, like why we're not approaching from this, we're approaching from the latter one, okay? So you have limit x approaching negative a, and then you have f what? You have fx minus fa, negative a, and then you have x plus a, because negative is positive, right? And so you have limit x negative a, fx. Now, obviously, this is an even function, so f a x plus a. Now, just like what we did in the past, we can actually use a variable to substitute. u is equals to negative x. And you're going to see why in a bit, okay? So if u is negative x, then you can say limit u is going to approach a instead of negative a. Why? Because you have x here. X, right? X tends to, x approaching negative a. If it is a negative x, the negative x is going to approach to a, okay? So, and then we have f this time, right? X is equals to negative u, so we have f negative u minus f a, and then we have, again, negative u plus a. Okay, so now we know that, okay, we got this formula, and then you have limit u approaching a, and we know that f negative u is just basically fu, no offense, and then you have fa, and then you have negative u plus a. Okay, so again, u is basically our dummy variable, and we're nearly done. So limit u approaching a. This time we can take away the negative sign from the bottom, so it becomes u minus a, and then we'll fu minus fa. And now we can also, what we can do is take the negative sign out, right? Then we can have all of this here. So I think this is pretty obvious because it is a dummy variable. We can change it back to x. X approach a, x minus a, fx minus fa, and what we're going to get. So we know that, okay, this entire thing is basically f prime a, right? So we're going to have f prime a. And so, given that, right, starting from here, actually, sorry, I didn't write it. But basically, we have just proved f prime negative a is equals to negative f prime a. So this is basically, again, proving that the derivative of an even function is an odd function. Okay, so this is part A, proving with both method A and B. Part B is similar. So part B is super similar. We just want to prove that derivative of an odd function is going to be an even function. Okay, so we know an odd function is going to go something like this, right? And so we want to prove f prime negative x is equals to f prime x. Super simple. Again, method A, method B. So method A, we're going to use f prime negative x. Okay, and then again, we're going to use limit h to 0, and then with f negative x plus h minus f negative x over h. And so we know that this is going to be in an odd function. So f negative x plus h plus fx, okay, because the negative sign came out. So we're going to have something like this, okay? And again, using the method of, input, output, right, we know that f, right, if we negative x plus h, if we times negative 1, the output is going to be negative f, and then the values inside. So we're going to have x minus h, okay, so we're going to have limit h to the 0, approaching 0, and then we have negative f, x minus h, plus fx divided by h, okay? And then using the dummy variable method, so we know that k is going to be negative h, right? And so h is going to be negative. So given that, okay, we're going to take limit k to 0. And, I've already explained that previously. We're going to have negative f x plus k plus f x, and then divided by negative k, okay? And so limit k to approaching 0, we can take the negatives from here. So we're going to have f x plus k, and now we can minus our fx. And then we also have negative k here. And so we can see that, okay, negative over negative, just cross them out, right? And cross them out, what you're going to get is limit k 0, and then you have fx plus k minus fx over k. And again, this is a dummy variable. We can directly change them to h0, fx plus h minus fx over h. This basically is our f prime x. So we've just proved, again, using method A, f prime negative x is equals to our f prime x. So this is how we prove with method A. Okay, and finally, so method B, we use the limit x to negative a function, right? And then we use fx minus f negative a, and then x plus a. Same thing. just like before. So now we take the limit of x approaching negative a, and then we have fx, and then we have to, so we know that this is going to be an odd function, so we're going to make this plus fa, and then x plus a. And obviously we have to change the sign here, right? So we use u again, u equals to negative x. So then we're going to have limit, our u is going to approach a, and then our f is going to become negative u plus fa, and then our x below is going to be negative u plus a. And so limit, so we're going to have u approach a, and then we're going to have, f negative u is an odd function, so we're going to have f u plus fa, and then you have negative u plus a. And here's quite obvious. We just want to take the negative side from both equations. So we're going to have fu minus fa, and then over u minus a, limit u approaching a. And obviously we also have the negative sign, but they got canceled out, okay? So again, this is a dummy variable. So we take the limit, we can change it by x to a, fx minus fa, x minus a. This is basically f prime a, right? So we have just proved, I forgot to write this one again. So we have just proved f prime negative a is equals to f prime a. So both of these have been proven. The derivative of an even function is an odd function. The derivative of an odd function is an even function. So, I mean, think about this, right? You have a curve here, and let's say, I'm going to get the negative side too. So an even function is always going to be this, right? It will never go to the negative sign. And so if you look at the slope here, okay. So this side, what is this going to be? This is a negative slope. And this side, what is it going to be? It's going to be a positive slope. Okay, so that's why it makes sense for the derivative of an even function is an odd function, and the way we mathematically prove is the one that I just showed you. But in graph wise, it kind of makes sense. And an odd function is going to look something like this, right? Odd function, something like this. Okay, and so we have the slope here, increase, 0, and then increase, right? So the slope here are positive, and that's why we've literally just proved that again in B. So I hope that all makes sense to you, and thank you for watching, and stay tuned for more.